Okay, so now we're going to start talking about hydrology, computing hydrologic parameters. So I've shown you, you know how to delineate a watershed now, right? You can either do it using the map-based method or the DEM-based method. But, and part of the delineating the watershed, you know how to compute the basin data. So you can compute your areas, your slopes, flow distances, things like that. Those are the basin data that you compute. That's called geometric parameters, geometric basin data. We can compute the geometric data. But what we have not yet computed, we have not yet computed the hydrologic parameters. And the hydrologic parameters are things like the curve number, infiltration rates, and the time of concentration and lag time for your watershed. So we're going to talk about how you compute those parameters for your watersheds. So we've learned how to do watershed delineation, DEM-based and map-based watershed delineation, and how to combine those two. So if we have some changes in our watershed, we can define our own streams, define roadway embankments, and things like that. Now we're going to learn about how to compute hydrologic parameters. And the parameters we want to compute are our loss coefficients, our precipitation, our time of concentration, and then routing parameters. We're not going to talk so much about routing parameters just yet, but we will later. So these are some of the hydrologic models that WMS supports. It supports statistical as well as deterministic models. And the deterministic models are what we call lumped parameter models. So we lump all the data for each subbasin into a single set of values. So there are statistical models, and the U.S. has statistical models for each state, and they've compiled years of data and figured out how to compute the flow rate for any watershed in the United States using all this historical data. And that's a statistical model. And that's called National Stream Flow Statistics. It's used in the U.S. And there are some parameters that are used in that model, and I'm not going to go too much into those parameters. Deterministic models, these are the parameters that you need. You need your rainfall values, your loss information. So your loss information could be the curve number, it could be your runoff coefficient, or it could be some infiltration rate. And you need some hydrograph routing parameters. So some way, not hydrograph routing, but your time parameters. So you need some way to figure out how long your hydrograph should be. And that's the time of concentration or the lag time. And so we know how to compute geometric parameters, but what we need to learn how to do is how to compute hydrologic parameters. These curve number, runoff coefficient, rainfall depth, and time of concentration. And to compute your curve number and other hydrologic parameters, you first need a drainage coverage. And you know how to get a drainage coverage because you just delineate a watershed using map-based or DEM-based delineation, and you have a drainage coverage. Other coverages you need a soils coverage, a land use coverage, and a time computation coverage. The soil and land use coverages are used for computing your curve number, your watershed curve number. The time computation coverage is used for computing the time concentration or the lag time. And these are the different things you can compute. So you can compute curve numbers, you can compute your runoff coefficients, travel time, and time area curves. There's an option in WMS. If I have a drainage coverage, you can overlay a land use file on top of that drainage coverage and compute the percentage of different land uses in your watershed. And you can use that for whatever you need to use it for. And you can also, if you have a rainfall grid, you can compute the rainfall for your watershed. So that's an option, but you probably don't have a whole lot of rainfall grids around here. That's in the US, they have a lot of rainfall grids. You can also define gauges, and if you define gauges, then WMS will compute these Thiessen polygons. I've already shown you how it does that. You define a rain gauge coverage, and it'll give you the Thiessen polygons, and then WMS, when you compute the basin data, it will assign those percentage of each rain gauge based on these Thiessen polygons. And this is what that looks like. Gauges can be used in HEC1 and in HMS. Either of those models can use gauges. You can also automate runoff coefficient coverage calculations. And the way you do that is you define this coverage that's called a runoff coefficient coverage. And the runoff coefficient coverage, you define polygons with different runoff coefficients. And then when you run the rational method, you guys know the rational method? It's Q equals CIA, where C is the runoff coefficient, I is the infiltration rate, and A is the area. That's the rational method. It's a very simple equation that's used to compute the flow rate, the peak flow rate out of a watershed. And you might not use that so much because it requires a lot of historical rainfall data. So to compute a curve number, you need a soil type coverage, a land use coverage, and you need curve number values for each soil type and each land use. So that's this table here. Once you've done that, you can overlay the land use soil type polygons on top of your drainage coverage, and WMS will compute a composite curve number. There's an attribute for a soil coverage called the hydrologic soil group. And there are 4 different hydrologic soil groups. A is for high infiltration. Soil group A is for high infiltration rate. Soil type B is for very low infiltration rates. So high infiltration rates would be sand or gravel. Low infiltration rates are clay. Usually have low infiltration rates. And you need data from the internet that you can download. And actually, don't follow any of those slides. That's how you download data for the United States. But we're in Egypt, so there's a couple places you can get data in Egypt. The easiest way to get data is from WMS. Let me read in a model that I have here. So here in WMS, if I'm here in Cairo in Egypt, if I want to get soils data, I can use this get data tool, or I can get data from map, either option. Let's do get data from map. And hit OK here. And then over here on the right, there's an option to download Harmonized World Soil Database, V1.1. Okay, and you select this. This is soils data for anywhere in the world. These other options, these 3 options, land use, soil shapefile, land use shapefile, StatsGo, and Surgo, those are for the U.S. only. So the U.S. has a bunch of databases of soil and land use. And so you can't use that. It's only for the U.S. This is for anywhere in the world. and so is the global land cover data. Yeah, so the source is, well, let's go to it. The name is called Harmonized World Soil Database. I can't remember where we got the data, but you can just go to Google and search for Harmonized World Soil Database. Go to the first one, usually, that's the best. And so it looks like it's right here. And it's version 1.2. Ours is version 1.1. Maybe we ought to update our data. So we haven't updated it yet. It takes a lot of work for us to go in and download the data, and then we have to get it, cut it into these blocks and update it on our website. But we're version 1.1. I think I've downloaded the data for this area. So if I go to this folder here, I'm not sure which one it is. I actually have 4 data sets with soils. They probably cover all of Egypt. But I'm just going to go to the first one, and we'll try opening it. So here's that one. Let's try another one. Maybe I got the wrong one. That's the wrong one. Let's go to the third one. Well, that's pretty much in the right location. So here's the Nile Delta right here, and here's my soils for that area. And you can go to this shapefile. If I want to see what the soils are, it looks like they're all the same. They're all clay, it says. So soil type is clay, hydrologic soil group D for all of the Nile Delta. Here's another one. This is probably for a water body like the Nile River, and it doesn't have a hydrologic soil group, so I don't know what you would assign to the Nile River. Probably D also if you wanted to use that. So let's see, let's go back to what we were talking about. Anyway, there's an attribute in the soil database that's called HYD-GRP. That stands for hydrologic soil group, and that's the type A, B, C, or D, and that's what WMS is going to use for your hydrologic soil group. And don't worry too much about these slides. These are for if you need to get the hydrologic soil group. The World Soil Database already has a hydrologic soil group in it, so you don't need to do any joining or anything like that. You also need land use data. So land use data, kind of the same thing. You can go to WMS, and in WMS there is this Get Data tool, and there's a global land cover database here. And so this is also on the thumb drives that I gave you. It's under the Egypt folder. The global land cover data, I downloaded it for the Nile Delta, so you can use that, or you can just get it online, get the online data. The problem with this is it's going to be a really large file because there are a lot of different polygons in it, but it's pretty good. The only problem is maybe it's not that great because it might not have the latest land uses. You know, there's land use changes, things like that. You may need to go in and edit your land use data based on land use changes. So you need land use data, and you can download that data off the internet. I'm not going to talk about that because that's for the United States. The other thing with land use data is there's a land use classification system, And for the world data, let me well, I'll show you how to use everything to compute a curve number later on here. We'll delineate a watershed, compute a curve number. I'll show you how to do that. But this is what a curve number table looks like. So you have different land uses, and then for each land use you have a curve number for soil type A, B, C, and D. So remember, D is kind of clay soils, A is the sand and gravelly soils, so high infiltration rates. And you have to have curve numbers for each of those soil types for each land use. If you have all that information, if you have a curve number, if you have a land use coverage, a drainage coverage, a land use coverage, and a soil type coverage, and then those two tables, then WMS will compute a composite curve number for each of your subbasins. So that's a composite curve number. You can, I'm not going to get into, does anybody use green and amped? Use the green and amped method? You do? You have. You need a lot of data. Yeah, exactly. So I'm not going to talk too much about this. The only thing I will say is later on when we talk about Geisha, which is our grid 2D grid model, you will, the only option, well, really the only option for infiltration in that model is the green and amped method. And I'll show you later when we get to that how to compute how to get the green and amped parameters. It's actually not that hard, but I'll just show you how it's done. Okay, so that's getting the loss parameters, so my curve number and my runoff coefficient, I can get those. I also need to get some time parameters, so my travel time, my time concentration, and my lag time for each of my subbasins. There are two ways of getting my time concentration and lag time. One way is just using my geometric data that I compute. When I compute my basin data, I can use that data, and WMS has a library of equations that can be used to compute the time of concentration or the lag time. Another way is I can define arcs that represent different types of flow in each of my subbasins. And for those arcs, I would define some equations on each arc, and the equation is different depending on the type of flow for the arc. So in the upper part of my watershed, I have what's called overland flow, and there's an overland flow equation. And then between that overland flow and the channel, I have something called sheet flow. And then along the channel, I have something called, well, it's just channel flow. And I can define Manning's equation for that. So if I want to compute the basin data using the basin data, compute the time concentration using the basin data method, WMS has a library of equations that can be used to compute the time concentration. And if I want to compute using the map data method, I can define these set different kinds of arcs. So I have overland flow arc right here, shallow concentrated flow arc, and a channel flow arc. For each of those types of arcs, I then define an equation in this window. And for the channel flow, it's going to be Manning's equation. The shallow concentrated flow has a different equation, and then overland flow has another equation. And I define those equations, and then WMS adds the total travel time up for a drop of water in each of those arcs. And that's the time of concentration for my watershed. Alright, so let's, actually I'm going to wait to do a demonstration, so we'll hold off. Before I do that, are you guys kind of tired? You're probably worn out. But, how do you deal with the swampy areas? So it kind of depends on what's happening in the swamp. If you have a lot of canals that are draining the swamp, then you have to account for those canals somehow. But if you if you're just modeling the swamp, then you would just use your regular model, you know, and you'd compute the amount of flow rate out of the swamp just like anything else. You'd have to define a curve number. Yeah, you define it as a swamp, and I mean, if you're not using the swamp, if it's just a swampy area and there's no development or anything in the swampy area, and that would be your land use, then you would define a soil type for the swamp. So type A, B, C, or D, and maybe it's clay, you know, if it's a swamp. So you would define that and your land use, and then you would compute a curve number, and you would just run your model just like any other model. For swamp, a lot of times you might want to use a 2D model like Geisha, and that will compute your flow depths, your overland flow depths, and that way you'll know what the depths are in the swamp instead of just running a regular model, running HEC1 or HMS and getting a hydrograph. So it might be better for something like a swamp to use Geisha. In fact, in Geisha you can define something called a wetland, and with a wetland there are different parameters you can define for a wetland, but I guess I'm not sure. So what are you trying to do with the swamp? Yeah, you could start out by just running HEC1. Just compute your curve number and try running HEC1 with it. And do you want to get the depths in the swamp, or like what do you want to get? Outflow. Yeah. So just use HEC1. You should be able to just use HEC1 or HMS, either one. And you'd use the soil type would be type D, which is clay soils. Okay, so we're going to move on ahead. And then we'll have a little, so the plan is the rest of the day I'm going to talk about HEC1 and HMS, and then I'll do a quick little demonstration where we set up a HMS model for somewhere close to here, and then I'm going to let you do the workshop, HMS workshop, and hopefully we'll be able to finish that today. Tomorrow we're going to do some other stuff, so let's go ahead here. So we're going to talk about HEC1, but HEC1 and HMS, when I refer to HEC1, it's also kind of HMS. Everything I talk about here in this lecture also applies to HMS. And except HEC1 is only for single events. So if you have a 24-hour storm, you can model that using HEC1. For HMS, you can do long-term simulations. We're going to talk about long-term simulations a little bit more tomorrow, about doing those. HEC1 is based on unit hydrographs, and there are a lot of different methods for unit hydrographs, for computing losses and things like that that are used in HEC1. And you can do stream and reservoir routing in HEC1. We're going to discuss those things. So in HEC1, this is a topologic tree that's used in HEC1, and I can model basin runoff. I can model combining the basin runoff at combined points, we call them. And then I can model stream routing and different things. So another thing I can do in HEC 1 is water diversions. I can model water diversions. So in HEC 1, there are several different things to set up. One of the things is the job control data. And this is the job control data for HEC 1. HMS also has job control data. And it's just basically the beginning and ending time for your simulation. There are some other things you can define in here also, but in general it's the beginning and end time of your simulation. And there's a time step. The time step is just used for computational computing as well as output. What's that? The time step? What should be used? It just depends. You can use as low of a value as you want. You probably don't even need to change the time step. This screen shows you that there's a 15-minute time step. I think that's the default in WMS, is 15 minutes. And that means a hydrograph point will be computed every 15 minutes. I could change that so a hydrograph point is computed every 5 minutes. It won't affect your model very much. The only thing that it's going to affect is it might affect your peak flow, because the peak flow might happen at a different time. And so you probably want kind of a lower time step, but 15 minutes is probably fine, or 10 minutes. You just need to be able to get the peak flow rate in your hydrologic model. So I don't know. Does that answer your question? It just depends. It's kind of up to you. But use something less than 15 minutes or less. Don't go over 15 minutes, I'd say, for your time step. Okay. Yeah, you want to get the peak. Yeah, the rainfall is a different time step. So to edit parameters in HEC 1, you just select your basins, your outlets, your diversions, whatever, and whatever you select, the thing that you have selected is the options you have selected are going to become available in this HEC 1 window. Same thing for HMS. You can select basins in HMS, go to the HMS, edit HMS parameters, and it'll show you whatever basins or outlets or whatever you have selected. It'll show you the parameters. The basin data that needs to be defined in HEC 1, these are the parameters. So you have to define precipitation, base flow, losses, unit hydrograph, and snowmelt. Actually, you don't need to define base flow or snowmelt data, but you do have to define precipitation, losses, and unit hydrograph. And most of the time, you may not have a base flow, or maybe you will. Like if you're doing the Nile River, obviously there's always a flow rate in the Nile River, so you're going to have a base flow. But sometimes you may not, and so you may not need to define the base flow. Snowmelt, you're probably not going to have a whole lot of snowmelt, but you may. I mean, you might be modeling the whole Nile River basin, and if you're doing that, then you'll have snowmelt in some places. But precipitation is, there are a lot of different ways to define precipitation in HEC 1 and HMS. A couple of the ways are probably the most widely used way is you define a total precipitation value and then a storm distribution. That's called a hyetograph. And for that, you just define a time series that shows you your rainfall, your incremental or your cumulative rainfall versus time. And then you define a total precipitation value. So how much does it rain in millimeters over a 24-hour storm? You would define that. Another thing you could do is you can define gauges. In gauges, you just define a rain gauge coverage. And for each gauge, you would define a total precipitation value. For one of the gauges, you define a distribution, and then that's your rainfall. Yeah, so I'm not sure about that. I know that you can use different rainfall distributions for different rainfall gauges, but I know in HEC 1 they did not recommend doing that. I'm not sure about HMS, whether they recommend it or not, so I'd have to check into HMS whether they recommend using different. So you're just asking if you can use different rainfall distributions in your model, right? Is that what you're asking? Yeah, so I think you can do it. You can define different rainfall distributions, but I'm not sure that it's recommended. I'm not sure that they recommend using different rainfall distributions. Yeah. I think you can do it in both HMS and HEC 1. Yeah, that's what you would do. So this is what a rainfall distribution looks like. It's just a time versus the distribution, and then usually the final rainfall value is 1.0, and then each of these values on the rainfall distribution is multiplied by the total rainfall for your storm. There are different ways of getting this distribution in. So to compute the unit hydrograph, the unit hydrograph is a hydrograph that just assumes 1 inch of rainfall over your basin. And to get the unit hydrograph, HEC 1 and HMS multiply that unit hydrograph, or to get your hydrograph, HEC 1 and HMS multiply that unit hydrograph by the total amount of rainfall in your basin. And so if it rains 2 inches, it'll multiply the hydrograph by 2. If it rains 0.5 inches, it'll divide the hydrograph in half, or multiply by 0.5. So that's a unit hydrograph. And I'm saying 1 inch, but it also could be 1 millimeter of rainfall. Yeah, so you can use Clark or Snyder method. And the Clark and Snyder method use something called a time area curve. And you can compute the time area curve in WMS. Maybe we'll look at those, look at the different options when we get to that. So we've already talked about how to compute a curve number. You need a land use and soil type coverage. And so there are a lot of different loss methods that can be defined in HEC 1, and these are all the loss methods. I'm not going to go over each of these, but just for reference, you have this slide and you can look at that. You can also do I'm going backwards. Okay, we've just talked about how to compute a lag time and time concentration, and what are the two methods for computing lag time and time concentration. There's one method called the basin data method, and the other method is called the map data method. And the basin data just uses your computed basin data and a library of equations, and the map data method uses time computation coverage, where I define the longest flow path of my watershed. I can also compute a time area curve, and this is used in the Clark and Snyder methods for unit hydrographs. I can also define routing parameters, and WMS or HEC 1 does channel and storage routing. Channel routing, I define my channel parameters, so I can define my length. In some of the methods I define a length and a velocity for my channel. In other methods I define the channel attributes like my cross section, and HEC 1 will use those to get my route, to define my routing. Routing is just, it lags and it also attenuates the hydrograph. And I had a graphic here that shows what routing is, but it's not working because I probably don't have Flash installed or something. But you can also define storage routing, and storage routing is just routing through a reservoir or a detention basin. And this is the equation for storage routing. Inflow minus outflow equals change in storage. The input parameters for storage routing is you have to have an elevation storage curve, and then you have to define your discharge at each of those elevations. And there are different ways of defining discharges, and I'll show you maybe how you can do that in WMS. So I can define my detention basin geometry in WMS, or I can just use the DEM to get my detention basin geometry or my reservoir geometry. I can also define weirs, outlets, and other outflows from my detention basin. And using this information, WMS will compute this curve that has my discharges at different elevations. It also has my storage values. And so the storage is in acre feet or cubic meters. The discharges are in cubic meters per second, or CFS, cubic feet per second. And this is what the curve might look like. So this is elevation, storage capacity, and discharge curve. So if I use a DEM, WMS uses the contours of the DEM or TIN to get my detention basin, elevation versus storage curve. For diversions, I define how much is going into the diversion for the different outflows depending on how much is going into the diversion. So I define this curve here, inflow versus diverted flow. And I can define diversions in WMS, and then those get transferred to HEC 1 or HMS. And the diversion can either be taken out of the watershed or put back in the watershed at some point downstream. Alright, so let's quickly set up an HMS model here. Yeah. I'll show you how to do both of those methods. Actually, I'm gonna read in some different. I'm not sure how good this elevation data is, so I'm gonna read in some different elevation data. Let's open in digital elevation files. So here's some elevation data. I'm going to run Topaz. So here are some watersheds that WMS gives me. Let me change my accumulation threshold. We'll just change it to 50 square kilometers for my accumulation threshold. Let's go ahead and delineate. So I'm going to just delineate a watershed. We'll do this one here maybe. Compute our basin data. Actually, let me recompute my basin data. One of the options, so when I compute my basin data, this window comes up. And this window gives me on the left side here, I have my model units. That's the projection. WMS just uses the projection that my data is in. So my model units are in X, Y values are in meters. It's using the UTM zone 36. My Z values are also in meters. My computed units are square kilometers for my areas and meters for my distances. One of the options, if I go to this button, Drain Data Compute Options, these are all the data values that WMS computes for each of my subbasins in my watershed. There's an option here to create a TC coverage. TC is time computation. So WMS can create a time computation coverage, and let's look and see what that does. So what that does, it creates this coverage that's my longest flow path in my watershed. So this is the longest flow path by distance, not by the time it takes or anything like that. This arc right here represents my longest flow path. So that's a TC coverage. I'll show you how to use that here in just a second. Okay, so I have my watershed delineated. Let's go ahead and set up an HMS model. Yeah. You can change, so you can manually go in and change this stream arc. For the what? Oh, right. Yeah, so I can change the stream, this time computation arc, however I want. It will not affect the watershed delineation.
Yeah, but as you just have shown, the longest stream is already defined in this watershed. So how could the time concentration change by changing something that does not affect?
You mean if I manually create a stream?
Not manually. If you go to this watershed and change the, let's say, show for that basin, the streams will maybe this stream will disappear. Okay? But the watershed will remain the same.
Yeah.
So that means that the WMS already understood that there is a watershed here, and I should go to the storage to determine my value. So how could the time concentration change by changing something?
You're saying if I change the flow accumulation? I'm not sure what your question is. Yeah, we'll talk about it. Okay. All right. So I have my watershed is delineated. Let's go in and define all of our HEC1 parameters. So I have part of the watershed that's down in this area down here. Let me turn off some of my display options. So I'm going to turn off some of these computed geometric parameters. I went to the display options and then to go to the projection right here. Display options. Oh, you're wondering how did I get the time concentration TC coverage? So you go to to compute drainage data, DEM, compute drain basin data. There's this drain data compute options button. You have to compute the basin data to get to that. Okay, so for watershed modeling, I need a few things. I need a curve number, I need a time of concentration, and I need rainfall values. So we're going to work on the curve number. So to get a curve number, I need soil and land use data. I have some soil data, but I need to read in one other soil file. So let's read in this last soil file right here. So here's my watershed down here. And I have soils data. I have probably soil data for most of Egypt, it looks like. All of Egypt. Okay, so I have soils data. I also have land use data that I've downloaded. I just used this get data tool, drag around this to download it. You can do that, or you can just open it. So my land use data, I think, is right here. Let's try this. Hopefully this does not take too long. So here's one of my land use files. Let's read in another land use file. This one must be a big one. It's taking a long time. So here's my land use data for the watershed. These are my land use polygons. Okay, so I have my soils, my land use data. I need a table that relates my soil and land use to curve number values. Usually what I do is when I'm using this land use and soil data, I will go to the hydrologic modeling wizard. This is just the easiest way to convert my land use soils data to. I have to convert this information over to the map module, to map module coverages. Let's turn on all my soils here. So I'll go to the hydrologic modeling wizard, and in this wizard there's a step called define land use and soil data. Select this step, and I'm going to create my land use and soil coverages for the drainage coverage. So I select drainage, that's the only option here. And I don't need to do anything up here. Everything is already joined. I have my land use types. If you go to the attribute table for this land use, each polygon has a land use type and a land use ID. That's the value. So I'm just going to go create coverages. I select the create coverages, I go next, and then I want to map the land use type to this value in the label right here I'm going to use. And then for these are my land uses. I'm going to map all those over. I'm also going to map my soil type data. And these are my hydrologic soil groups. So types A, C, and D are in this area. And the wizard's creating my map data, land use, and soil type coverages. The coverages are for just the area that's inside of the watershed. So the wizard, if I use this hydrologic modeling wizard, the defined land use soil data, it creates, as long as I have land use and soil data in WMS, if I select this button, this wizard will create my land use and soil type coverages, and it will clip them to the watershed boundary. Okay. So what I have here, this is my watershed here. This is my land use coverage. So these are my different land uses in the watershed. These are my soil types. And each of these, I have all these polygons. So here's a polygon that represents soil type. And that's soil ID 4, which represents clay loam. It's type C soil. Okay. And so that's how I get my land use and soil type coverages. Another way you could do it, and I didn't want to do this just for time, but you could go to the GIS data module. You can drag a bot. You can turn on the coverages you want to create data for. So I could turn on these soil coverages, create a new soil coverage here under my map module, drag a box around the soil polygons I want to convert to the map module, and then go to this mapping, map shapes to feature objects command. But all the stuff in the hydrologic modeling wizard, that step in that wizard does all that stuff for you. So you just hit the create coverages command, it creates the coverages, does the mapping, and you just follow the wizard, and it will help you. Okay. So I have my land use, I have my soil type. I'm pretty close to being ready. Let's go to calculators, compute GIS attributes. And the first thing here on this list is I can compute SCS curve numbers using WMS coverages. I'm going to use the soil type coverage for getting my soil type, land use coverage for getting my land use. And then I have this table that relates the different land use IDs to curve number values. Right now, it's filled with zeros. I have no curve number values in my table. So I need to get curve number values. Well, let's hit the help button here. See if I can get any help on this. I'm getting these curve numbers. If I hit the help button, then WMS brings up a website on the XMS wiki that has information on downloading a curve number table. I can get this curve number table. So if using global land cover data as a shapefile, download and use this table. So I'm going to right click here, select save, link, and we're going to go to the documents. We'll just save this out to a file. Okay, then I can go into this compute GIS attributes and I could read this file. It's going to tell me that this is going to overwrite what I already have. That's fine because this is the global land cover data table and it's what I want. So here's that table that I read in. So here are the different curve numbers for each land use ID. Okay. So this is what I'm going to use to compute my curve numbers. Hit OK here, and WMS creates this curve number, runoff curve number report. So these are the different hydrologic soil groups in my watershed. These are the different land uses. And this is the curve number that goes with each of those combinations with the hydrologic soil group and land uses. And these are the different areas that those combination of soil group and land uses are. And then it adds these products up, curve number, takes the curve number times the area, adds all these up, divides by the total area of the watershed, and that's my composite curve number, so 77.016. I don't know if it's that accurate, but that's how we get it. And then it will assign that to my HMS model. Okay, so I'll be able to use that in HMS. The other thing I need to get is my time of concentration. And so let's go to HMS. Let's change the model here to HMS. We're going to bring up my basin data for HMS. So we'll define a loss rate, and the loss rate we're going to define is the SCS curve number method. There's my curve number that was computed. I also need to define a transform, and the transform is just the unit hydrograph method. And there are several different methods. Let's just use the SCS unit hydrograph method, but you could also define a Clark method. Maybe we'll look at that later. And for the SCS method, I need to compute a lag time. And I can compute it using either the basin data or the map data. To compute using the basin data, that's as long as I have some basin data computed, then I can just do the basin data method. One of the options here is to compute the lag time using the SCS method. This uses your watershed curve number, the watershed length, and the watershed slope to get the lag time. And this is the lag time that's computed, so 25 hours, pretty long lag time. I don't know how accurate that is. And then lag time is going to vary widely depending on which method you select. So for example, this Denver method, lag time is 19.74 hours. Tulsa, 13 hours. So it just varies quite a bit, but we're going to use the SCS method. Pardon? Say that one more time. I'm sorry. Oh, okay. So you're saying you use the Riverside Mountains method? So 10.49 hours? Okay, we can do that. The other way to compute your lag time is you could use the map data method. And right now, okay, so the way you do the map data method is the first 100 feet in your watershed, you define that as sheet flow, which is also known as overland flow. From there until you hit your stream, you define that flow as shallow concentrated. You use the shallow concentrated flow equation. And then wherever you're in your stream, you use the open channel equation. The open channel equation is just Manning's equation. Do you know about Manning's equation? Okay. And all the equations are here in the dialog. If you're not sure what the equation is, you can just look at it. And these are the different equations. There are different versions of the sheet flow and different versions of the shallow concentrated flow equation. There's the TR55 method and the FHWA method. This is the US FHWA method. You could use either version, probably. They may give you similar results, but I'm not sure. So what I usually use is the FHWA method. And the problem is when you create the time computation coverage, it does not split your arcs where it hits the stream and then at the first 100 feet. So what you need to do is go here in the time computation coverage. You need to measure 100 feet, which is 33 meters, 30 meters basically. And for that first 30 meters, use the measure tool here. The first 30 meters, define that using the shallow concentrated flow equation. It's going to be a very short distance. So I'm going to split this arc right here. Then I also split the arc where it hits the stream. So here's the stream. I'm going to add a node there and split that arc there. Then I'm going to define, go back here to HMS, and we're going to define an equation for each of those arcs. So I'll go to the map data. And so for the first arc, we'll go to edit arcs. This is my shallow concentrated, or my sheet flow equation. And define a Manning's roughness, so whatever, something like 0.1 would probably be a good value. Define a rainfall intensity. And, you know, I'm not sure how you would get this. You would just define, do you know how you'd get it? The rainfall intensity? Yeah. Okay. Overland, shallow concentrated flow, and yeah. So let's just say, put a value in here. So that's my time for that, time of travel for that arc. I can go to this second arc, define my, this is shallow concentrated flow. And there's a manual where you can look up an intercept coefficient. I'm going to do 0.2. That's my, and then I get a travel time for that arc. I'm going to go to this final arc. And we're going to define that as open channel flow. We'll find a Manning's equation for that one. So, or Manning's coefficient. And hydraulic radius. And you can use this calculator to compute the hydraulic radius. I'm just going to enter it here. And we can do it for that arc. Oh, sorry. This one's sheet flow. So 0.1, and we did 30 for that one. Arc 2 is shallow concentrated, 0.2. And then arc 3, we're going to do open channel. So 0.045. And then we'll do a hydraulic radius of 2. Okay? So I just entered them on the wrong arcs. So WMS will add up the times for each of these arcs. And that's my total travel time for this watershed. And that's the time of concentration. Okay? Yeah, I add this travel time plus this travel time plus that travel time. That is my, and you can select whether you want that to be the lag time or the time concentration. It's usually the time concentration. And then, so the 48 hours, when I hit done here, it'll convert it to a lag time for use. So it'll convert it to a lag time, 28 hours. 0.6 times the TC. You can just use the basin data. So what I was saying, there's two different methods. One is the map data. That's what we just used.
We use map data.
That's a lot harder.
If I use a map for creating the boundary of the sheet and network, the DM is not there. I don't have the DM.
Yeah, so you might want to use the map data in that case. So, I hope I didn't confuse everybody. Did I confuse everybody?
I don't know, but too long.
It's too long.
Yeah.
Okay. All right.
Just click on the basic.
Just click on the basin data.
Okay.
Yeah, and then go
Sometimes
to
I use the
Riverside Mountains.
Sometimes we
Okay.
use modified equation. And modify the equation.
Use which equation?
Modify the equation.
Modified?
Yeah. Here in the other form, the right form. Here we have modify equation.
Modify. Oh, you modify the equation.
Yeah.
Okay.
Sometimes just to modify to give value for the constant.
Okay. Okay. Yeah, so you can do that. But you just modify however you.
Wouldn't we stop here at the maximum slope and give the value so we can use the computer calculator if it's not there?
Yeah, you can change. You can.
Can I define these values if I use a map?
Yeah.
I can define the value
You
here
can define it
and
on your own
ask-
instead of
yeah.
using the computed value.
And you can substitute the equation directly.
Yeah.
When you have a request, the SES, you include only the 24-hour distribution for the SES. Can you include the rest of the SES distribution, like 6 hours?
Yeah, we can do that.
Yeah.
We don't.
Yeah. Can you do it?
I can put in a request. Where do you get them? Where
When
do
I
you
use 24-hour, I get a notice or a comment that 24 hours is not suitable for our area. I like to use 6 hours, so each time I have to import the table for the 6 hour distribution.
It's the 60-hour distribution?
6.
6 hour.
Yeah.
6 hour, okay.
Yeah, 6 or 3 or 4 hours.
Okay.
Little, because in Arab area we don't have long duration.
Okay.
We have short duration.
Yeah, we can do that.
Yeah.
So I'll look it up, and we
I
can
get
probably
the table from through the internet. I get the table.
just on the internet.
Yeah, but I needed to create edits.
My understanding is using a graphical app.
Mm-hmm.
So you do an app and you divide it
Yeah.
into
Yeah.
segment equation.
Yeah, you define an equation for each segment. That's just it's just a different way of computing.
Divide the watershed into 6 sections. Maybe by the slope or something. And after preparing that computation, in each one, the total time computation will be the summation of
Just add them up. Yeah. That's what I was doing. Yeah. And it's a lot harder. But sorry if I confused everybody. But I guess what I'm saying is to compute the lag time, probably most of the time you could just go to this basin data method. So go to basin data, compute using the Riverside Mountains method. Okay, and then hit OK and it puts it in there. Okay. So I'm not done yet. I'm almost done. The other thing I need to do, I've defined there are 3 main things I need to define. I need to define my losses, which is my curve number. I need to define my lag time. The other thing I need to define is my precipitation. The precipitation shape files? Soil type and land use, they're on your computer under the Egypt directory. They're also you can download from WMS, and you just use this get data tool. What's that? It covers the whole world, yep. The whole world. Anywhere in the world. Soil and land use, yep. I don't know.
No, I don't think so. Normally for the source data, especially for our country, you cannot
Okay, so so you want to know how to download the gauge information from the internet? Well, all right. Maybe I'll show you that later. We'll show it to you later in the course. I think right now we're just going to enter a value. How do you get precipitation for your model? How do you do that? You have gauges, and do you have if you need to design a road, like if you have a culvert that you're designing for a road, how do you get the flow rate or the precipitation for that watershed that contributes to that culvert? How would you do that? Time series. You just have historical precipitation, and you have to create. You have to analyze that and get do a statistical analysis. So you don't have all that, the statistical analysis already done everywhere in the country. You have to do it yourself. Okay, so it's a lot of work. In the United States, they have, let me show you this. I mean, I don't know if somebody wants to think about doing this for a PhD topic or something, but there's something called NOAA Atlas 14. And so the United States, you can go to anywhere in the United States, and like say I'm in Florida or something, and then this map, this Google Maps is going to come up, and I can select the location where I am, and this window will give me the precipitation at different durations and recurrence intervals for different storms. So these are all my different storms. So this location in Florida, for my 500-year storm event, my 24-hour precipitation is 15.2 inches. This is only in the U.S. So you might want to think about somebody putting this up in Egypt. I don't know. If they do, then we can maybe put it into WMS. Yeah. This is the idea, yeah. So.
WMS can help us to create this table. We have some gauges and we have some data.
WMS isn't really designed to help to create this. There are other programs that you would use to create this. There's a program called the HEC puts out. There are a couple of programs that they put out that will help you to create this table. But anyway, we could talk about that later. Let's finish up here. So we're going to finish up our HEC1 or our HMS model. So we'll go to HMS to find our meteorologic data. And there is this button, download precipitation from web, but it's only available in the United States. The selected location is not within the bounds of the data. You're going to get that error message. But I'll define a hyetograph, which is a graph of precipitation versus time. And then I'll just define a total depth. And this is in inches. So I can change, so I define it in millimeters. I'm just going to do inches. We'll say it's 4 inches for this storm. Okay. And then I just save my HMS file. So we're going to save this out. WMS will save the HMS file. And HMS is a separate program. It's not a part of WMS, a separate model. So I'm going to run HMS. So HMS should be installed, I hope. Let's see, HMS. Yep. 4.0 is the version we're using with WMS 10.0. So I'll start up HMS, and we'll be able to run this model in HMS. So here's my HMS model, and when it brings it into HMS, you can see here's my watershed. So HMS is a graphical program. I have a watershed here. I can select the run I want to run. I run it. These are whatever messages I get. You can see them down here. And then I can get a hydrograph here. No hydrograph. Well,
maybe the 4 inches to
yeah, maybe not enough. So it looks like, oh, my precipitation wasn't. For some reason I didn't get my precipitation. Let's go, make sure I've defined precipitation here. It's 24 hours. Anyway, that's how you set it up. I'll work on this and try to get it running, and we'll get back with you. But I guess we have 20 more minutes for today. So maybe what we can do is get started. We have a workshop. The first workshop we're going to work on. It was a long day, I guess. The first workshop we're going to, looks like it was a long day for you especially. So we're going to work on the HMS workshop, which if you go to your files here, under your files there's a PDF. Under PDF, we're down on lesson 9, and there's a workshop called HEC HMS Interface. We're going to do that workshop, and